we need those for wind vulnerability analysis. However, the weather prediction models, such as those of Pag-asa, can only forecast these sustained winds. Moreover, wind exposure affects these wind speeds by amplifying and diminishing them, so the actual wind speeds recorded are affected by wind exposure. Therefore, we highlight the need to convert the sustained winds, the forecast sustained winds, to 3-second gusts while also factoring in the wind exposure. So with that, the general objective of the study would be to develop or to calculate those conversion factors, the gust factors. Specifically, quantify the wind exposure, recommend exposure categories, and to hindcast those gust factors. Once those gust factors are calculated, they will be useful in impact-based forecasting and anticipatory risk assessment before a typhoon hits. We can also improve our current wind maps. So, the context of the study is that we are in the atmospheric boundary layer where surface friction is the number one main cause of turbulence. This turbulence strength depends on these three factors, where wind exposure or the local conditions would be further dependent on these four factors. Please note that in this study, the surface roughness is delineated to exposure categories. So turbulence also causes the mentioned gusts, which are destructive. The gusts also depend on these three factors. Since these gusts are destructive, we want to forecast them, and we will be using an empirical statistical approach in this study, which is the gust factors approach. So to show some studies that have used the gust factors approach, here are some studies, as well as their locations and stations. So the important thing to note of is that after calculating the gust factors, they stratified these according to these parameters which were found to affect the gust factors. So that's what other studies have done. This is what my current study will do. We start with the coordinate and elevation of each Pag-asa station to calculate the topography around each station. So we get the sustained winds, and then using the birth and time stats of typhoons, we request for the 3-second gust wind speed. And that also comes with wind direction for the wind directionality. Afterwards, we classify each Pag-asa station into 3, Wiringa, Harper, and SCP. And then after that classification, we remove the wind directionality and topographic factor from the gust to get the flat surface gust. These gust factors will come from the flat surface and the simulated winds. These gust factors will be compared with existing gust factors, but from Harper. It will also be validated using actual data, and then they will be stratified using roughness length, and then double stratified with these 3 other factors. So, performing that methodology, we used 35 Pag-asa stations from these years, and we requested the gust direction and pressure. After cleaning the data, we are only left with 1,100 or so. So this is the 35 stations, and that's the terrain profile used for the topographic factor. We group the Pag-asa station directions into 3, Harper, LSCP, Wiringa. We start with Harper. This will be useful since, as I said, Harper developed or proposed gust factors for exposure categories. But only 2 exposure categories are applicable to the Philippines inland of sea. It's here, I think it's swapped. 1.38, 1.66. We compare what we have found in the study, which is, so for the inland, it's quite close, but for the off-sea, it's a bit quite far. So we also stratified them by sustained winds, which will be discussed later. Next, I said we classified not only by Harper, but also NSCP and Wiringa. So here are the resulting gust factors per exposure category based on those 2 classifications. So now we investigate the influence of the roughness length on these gust factors by plotting it with increasing roughness length. So as can be observed here, as we increase the roughness length, the gust factors also increase, and that actually agrees with the literature. However, for Wiringa, the gust factors appears to be invariant or actually independent of surface roughness, which does not agree with the current literature. So this is only the effect of roughness length only. So we double stratify after roughness length with wind speed, so per exposure category, and then we observe that for NSCP, the wind speed actually decreases as the gust factor decreases as the sustained winds decrease. So we can actually observe this with a better graph here. So this is the mean wind speed graphed with 2 standard deviations above. As we can see, as the wind speed decreases, the gust factor values and also the variability, it actually becomes thinner also decreases. So this agrees with the current literature, so as shown here. And also the spike at the end was also modeled because this was attributed to the lack of data at higher wind speeds. So this that process was repeated for Wieringa or the modified Davenport classification, which also yielded the same observations. That's also repeated here. And now we investigate with another parameter, which is the distance from the typhoon center, since we are considering cyclonic gust factors. So there is a decrease in gust factors as the center of the typhoon approaches, and it also agrees with the findings earlier. Next, we also check for altitude, and for altitude, it actually agrees. As the altitude increases, the gust factors increase. It also agrees with our earlier results that because at higher altitudes, the winds are also increasing. So now to quantify those relationships that I mentioned, we perform multivariate regression analysis for NSCP and Harper, and to be we set the p-value to be 0.05, and if it's lower than 0.05, the relationship is actually dependent. Just to summarize, the factor that is most, not just for NSCP and Harper, the factor that is most not dependent or did not show much dependency, gust factor would be the central distance. Okay, so now we try the operational forecast. So as seen here, if we stratify the gust factors with reference length only, and if we double stratify with wind speed, central distance, and altitude, one thing to be noticed is that the errors decrease when we stratify. So to conclude, so we can improve our forecast if we know that we are in high altitude areas, that the difference between the sustained winds and the gust will be decreasing. But if our location would be from rougher terrain, that large gust will be expected. So, and then gust factors can also be operationally used alongside the Pag-asa weather research and forecast. And we recommend to increase the scope of the data, as well as to use objective actual roughness length values, and to use temporal variability, to investigate temporal variability. And with that, here are my references. Thank you for listening.